25 years after the first experimental demonstration of attosecond pulses, the field is transitioning. Researchers are now pursuing the active, coherent control of electron dynamics. This involves active steering, using synthesized light transients to control the motion of electrons in real time. Achieving this level of control requires moving high harmonic generation technology out of specialized laboratory environments and into broader applications. The primary technical barrier to this expansion is the low conversion efficiency of the standard HHG process. Unlocking the next stage of attosecond physics is a rigorous engineering optimization problem. Researchers need to push HHG into the extreme ultraviolet and soft X-ray regimes, specifically to reach the water window required for biological and chemical probing. Generating these high photon energies requires driving the system with longer wavelength mid-infrared lasers. This data illustrates a consequence of using mid-infrared drivers, a sharp decline in conversion efficiency as we approach the soft X-ray range. In this high-energy regime, traditional dispersion compensation and phase matching techniques are no longer effective. Overcoming this bottleneck requires a multi-dimensional optimization approach. We have to address the problem across 3 dimensions: the microscopic single-atom response, the spatial beam properties, and the macroscopic phase matching conditions. Optimizing only one of these factors in isolation will fail to produce a high-flux beam usable for practical experiments. The zero-dimensional problem focuses on the single-atom response, specifically the 3-step model of an atom in a strong laser field. In a standard scenario, a single-color driving field creates the electron trajectory shown in panel A, leading to the return energy curves in panel B. By introducing a tailored 2-color driving waveform, we can intervene. Panel C shows how adding a second harmonic fundamentally changes the electron's path. This intervention enhances ionization and recombination steps. The flattening curve in panel D indicates a higher cutoff energy. Engineering the field at the subcycle level allows us to multiply the photon yield before the light even leaves the atom. The 2-dimensional problem concerns the spatial geometry of the harmonic beam as it propagates. A common misconception is that the harmonic wavefront is a simple replica of the driving laser. In reality, the spatial intensity profile of the driving pulse induces chromatic aberrations. This spatiotemporal poppling creates the divergent paths shown here. Depending on the target's position relative to the focus, different harmonic orders originate from real or virtual source points. Without correcting these spatial aberrations, researchers cannot tightly refocus the beam for nanoscale imaging, regardless of the single-atom efficiency. Finally, we reach the 3-dimensional problem: macroscopic phase matching through a volume of gas. For efficient generation, the phase velocities must remain locked to the XUV field over the length of the medium. This phase lock is disrupted by dispersion from neutral atoms, the presence of free electrons, and specific focusing geometries. These geometric scaling rules are mapped on this hyperbola. It shows the necessary trade-off between gas pressure and the length of the medium to achieve high conversion efficiency. Researchers must navigate this curve, balancing high pressure with short media to avoid the reabsorption of the generated XUV photons. Phase matching is a fragile equilibrium. Excessive ionization creates plasma that breaks the lock and stops the harmonic buildup. Conventional gas media setups often lack the precision to maintain this equilibrium for soft X-ray generation. Glass microfluidic devices offer a solution. These chips are specifically adapted for extreme laser-matter interactions, allowing micrometer-scale control over gas flow. This precision enables the exact pressure gradients needed for quasi-phase matching. These chips also function as waveguides. By selecting specific waveguide modes, researchers can reshape the fundamental laser field. This allows for the continuous correction of spatial intensity and phase mismatch over long interaction lengths. Microfluidics creates a physical lab-on-a-chip that solves the spatial and macroscopic optimization problems at the same time. There is an alternative: abandoning the XUV generation process entirely. For years, it was assumed that a visible light pulse could not be shorter than one of its own optical cycles. However, a multi-octave continuum spanning from near IR to deep UV provides the bandwidth necessary for sub-femtosecond waveform confinement. This photograph shows the synthesizer required to achieve this. Pulses are broadened in hollow core fibers. split into spectral channels, and precisely recombined. We use attosecond streaking to verify the result. These panels show the spectrogram and measured duration of the synthesized pulse, approximately 380 attoseconds. This method delivers attosecond resolution without the efficiency losses inherent to the XUV harmonic process. Visible light synthesis bypasses the water window bottleneck, providing a new path for all optical spectroscopy in solid-state materials. Both pathways, optimizing HHG with microfluidics and synthesizing visible light waveforms, are converging on a shared objective. The goal is the complete sub-cycle sculpting of electromagnetic fields. This will allow us to image chiral dynamics in biomedicine and precisely clock electron transport in next-generation semiconductors. Attosecond science has matured into a sophisticated engineering discipline that uses structured light to rewrite the behavior of matter at the quantum level.